Here's what that might look like if you introduce async code. So we're able to take the request and immediately pass it off to the SQL database, but we no longer care as much about the fact that the query is going to take a long time to run, because we can, while the SQL engine is handling the results of the first query, we can handle the second query and go ahead and fire that off to the SQL server. And it gets its results back, and then we can return that actually to the second user before we return the results to the first user, depending on what order they come back. So this allows you to handle more requests at the same time, more throughput for your servers. And typically each server is going to be running somewhere in the neighborhood of 5,000 threads, right? So you might be thinking, well, I've only got a couple hundred users. I don't really need to worry about this. But you got to think about the fact that web pages are usually more than just one single request per page. You've got CSS and JavaScript sometimes. You've got AJAX requests. So you've got lots of requests that are happening for all of those users. Not to mention they're probably going to be visiting multiple pages on your site over the course of their session. And especially in the age of cloud computing, right? You don't want to be unnecessarily spending a huge amount of resources on cloud servers and having to scale up to 30 and 50 instances just because you've got inadequacies in your code that are preventing you from handling these requests concurrently. So here's what it looks like for a UI application, like a Windows desktop application or a mobile app. And so the user is going to click a button in this example, so the user's on the far left. Then we've got the operating system as the second one. We've got the UI thread, and then we've got the web server. And so just like in our previous example in the web, where we kind of had an imaginary scenario where we only had one thread, in a UI application, you only have one UI thread, right? And so you have to kind of protect that thread from being blocked. So in this case, the user clicks a button which sends a message to the operating system. The operating system then sends a message to the UI thread of the app, through the message loop. And in this case, we're going to do an HTTP request to some API over on your web server, right? And if that takes 20 seconds to come back, that means that we're blocking the UI thread for that full 20 seconds, right? So what happens then, in the meantime, is what we call the curtain of patience. So then you get the response back, and then finally we're able to actually do things with the screen. And so if you guys have seen this before, this is what we call the curtain of patience. That means that the UI thread is blocked doing something. The OS is trying to send it messages and it's not able to respond to them. So you definitely don't want that. You want your app to remain responsive. Most likely, if you're waiting on a web request, you probably want to show some spinner or loading indicator of some kind. And that spinner and loading indicator isn't going to update on the UI thread if the UI thread is waiting on that request to come back. So you have to do things asynchronously. So here's what an async UI application is going to look like. Same thing, we've got the click button going from the user to the operating system. Operating system sends a message to the UI thread, which kicks off the HTTP request. But we can return, the UI thread can return and tell the OS, yeah, I'm handling it, I'm good. And in the meantime, as we're waiting on that request to come back, the OS can send more messages to the UI thread, which you'll see in an example here in a little bit of things like, I want to move the window or resize the window or do other things. And it can keep handling those while it waits on the request to come back. And then finally, when the response comes back, we want to be back on the UI thread to, most likely, we're going to say we need to show the results of a query or something on the screen. We need to do that back on the UI thread. So we return the UI thread and then handle that the next time we get that message loop back. So that's kind of what an asynchronous UI application looks like. And so I'm going to be doing all of my examples with the UI application because it's got a single thread. It's easier to reason about and kind of easier to understand. But a lot of these apply to the web as well. And I'll show you a couple techniques of what you can do in the web with ASP.NET MVC and Web API with async code. So before we had async and await. So we're going to get to async and await in a little bit, but this is kind of the history of asynchronous programming. And I'm skipping forward a little bit, of course, because this is C# code, and C# is a relatively new language in the history of computing. And before then we had threads and C++ and everything. You even had threads in C#, but this is kind of the first time that we started seeing a way of not having to think as much about the thread in C# code. And that was through iasync result. So how many of you guys have seen this before? And all right, cool, a lot of you. So there's a number of different ways of handling an iasync result. You can pass it around. It's just kind of a handle onto some sort of asynchronous operation. And anytime you see the begin invoke, usually that's going to be returning an iasync result. And then it's going to do something most likely on another thread or as a result of an asynchronous operation like doing an I/O. which is another point. Just because something is async doesn't necessarily mean that it's happening on another thread. Sometimes it's coming back as a result of an I/O completion port. So that's a little more of an advanced concept that's a little low level, but I encourage you guys to look up I/O completion ports and how they work, and that kind of gives you some indicators as to why you want your I/O to be asynchronous. And then what I'm doing here is terrible. This is a bad example, because what this is going to do is this is actually going to block that thread until it's done. So this is just an example of how you can actually interact with that wait handle. Say it was on a different thread or something like that, but it just kind of gives you an object kind of to reference for the results of that async operation. Then we had TPL, so Task Parallel Library. So that was introduced with somewhere around the time of .NET 3.5, I believe. And I think they had some of that a little bit earlier, but basically you can see on the left we've got a method called doSomethingAsync, which returns task. And so task is used heavily. The same TPL task is used with the async and await keywords as well. But we call doSomethingAsync, but since we don't have async and await yet, we have to call methods like continue with. To basically say, once the task is done, then we want to execute this Lambda, which is going to happen at some point in the future once the task is done. But again, this is a bad example because we're waiting and we're blocking the UI thread. So don't do this. It's just an example of how you can actually get this to work in like a console application. But then in this case, as soon as the task T1 finishes, we call console write line to say, hey, we're done. Then we do something else async, and then we call continue with, and then we've got another Lambda. And so you can see where if you start having more than one async operation, you start ending up in kind of like a cow's head shape, right, of this kind of arrow shape of nested Lambdas. And that looks very similar to how a lot of people have been writing JavaScript up until this past year, right, where you've got var T1 equals do something async. Well, you get a promise back, right? A promise is essentially the same form as a task. And then we call then instead of continue with, and we give it a function. But you can see that it's very similar to the JavaScript approach of how you would do that with promises. So then we get to async and await. So you can see that this code is identical functionally to this, but we don't have to call wait in this case. The caller is going to be doing that either implicitly or explicitly. And so we've got do something async, do something else async, but in between there we're coming back and we can add our synchronous logic like calling console.writeLine or anything else. And so this is much cleaner than this, of course, and a lot easier to reason about. The other thing too is if you try to do error handling over here, it's a bit more interesting because you've got to check to see if an exception occurred and everything like that. Here you can just wrap that await in a try catch, right? So hopefully this, for any of you that weren't familiar with async and await and why you might want to use that, hopefully this is kind of a good overview. And so now we're going to move into kind of how this works under the hood. So with an async method, and this is from Microsoft's documentation, so I generously borrowed it from them. But you can see that a simple looking method with async and await becomes very, very complex in terms of how it operates. So we start with a click handler that comes in as number 1 at the top. I know it's a little hard to read, but basically we come into the method, which is async task event, access the web async. And then we do some synchronous things like new up an HTTP client. Then we call client.getStringAsync. But in this case, we're not awaiting it. We're just getting the task back. Awaiting it unwraps the task to get the underlying value if it has one. But in this case, we're not awaiting it, so we're just getting the task back, which means that all of this continues to operate synchronously until we get to the first await keyword. Now, client.getStringAsync is doing its work asynchronously, but you'll notice that there's 2 returns from that. So HTTP client getStringAsync at number 3, which is the orange line, returns the task as soon as it can. So basically, as soon as it gets through its first synchronous code within that method, it returns back the task event, and then it goes off and does something asynchronously, such that once that asynchronous operation comes back, we get essentially kind of another return, which is what happens at the end of the task. So we get a task back immediately, and then we get some result in the future. So there's 2 things that are returned from the method. And then, but in the case of the await, which is down here, where we call string URL contents equals await get string task, because we're actually awaiting that task now, We're waiting for it to finish, and then we get the result back, which is a string in this case, and then we return the length, and we can do any other synchronous or asynchronous code from there. So very simple async and await keywords get translated into something very complex. In the original planning for this session, I really wanted to get into kind of how this is implemented at the compiler level, but I don't have enough time for that. So, but basically it creates a state machine under the hood. So all of this gets translated down into essentially a series of structs that have state machines and like ints as to which await you're getting to, and it basically switches on that, when it comes back and everything like that. So if you guys are interested in how all of this works, I recommend you check out John Skeet's blog. He has a series of posts called EduAsync, where he goes through, he started it back when it was just in CTP, so some of it has changed since then, but back in the CTP days it was also a lot simpler, so it's easier to understand. But he goes through actually how that's implemented, how you can actually implement async and await yourself, because just like with how for each expects something to be, have a method that has get enumerator, and so you can kind of implement your own IEnumerable and IEnumerator. Same thing is the async and await keyword expects something that has a method called get awaiter, and so you can actually implement your own awaiter and everything like that. I don't recommend you do this for production applications, but it's just if you're interested in compilers and how they work and how async and await works, it's a good exercise to go through. So sometimes people aren't sure whether something should be made async or not. So you saw at my title slide that I said async all the things. That's not entirely true. So don't async all the things. There are certain things that you should, and basically if that's I/O driven, by all means async it. And that means anything from file I/O, but also network I/O. So that means HTTP requests, WCF or any kind of socket networking, SQL queries. SQL queries are going out over the network, so that means you've got networking involved. So unless you're using something embedded like SQLite. But basically, if you're doing any kind of I/O, absolutely async it all day long, please. It'll pay off in the long run. There are times when you're probably not going to want to async things just because you can. It's very easy to just wrap code in task.run in a Lambda and kind of throw that off to a background thread and await that, right? But you probably shouldn't do that unless if it's a UI application. So in a web application or some sort of service, don't worry about awaiting any kind of CPU-intensive tasks and putting them on a background thread, because you're actually creating more overhead and you're going to slow things down and you're not helping your concurrency. So in the case of CPU-intensive tasks for the web, don't async that. Just let that run synchronously. But in the case of UI applications, Android, iOS, Windows, anything else, you are going to want to do CPU-intensive tasks on a background thread, such as like image resizing if you're trying to resize thumbnails down or things like that. So you probably are going to want to do that in that case. But things like UI manipulation, HTML rendering, don't worry about asyncing that. JSON.NET, the library for .NET, used to have a deserialize object async method. Still they do, but it's marked as deprecated because they kind of realize there's no point really in doing JSON deserialization asynchronously. You should be doing the synchronous methods of that. So they kind of wised up and made that deprecated. So there's three types of return types for async methods. So and again, async methods are denoted by the async keyword, and the compiler is going to expect it to be one of those three types. So you can get async void, async task, or async task of t. Now, most of the time, actually, I'm just going to go ahead and say this. All of the time, with maybe a slight caveat, every blue moon, in a web application, you're going to be using async task and async task of t. So if you're writing async void for a web application, slap your hand, ask yourself why you're doing it. You probably shouldn't be doing it, okay? Because you're almost always going to want to await the results of that. Async void is essentially fire and forget. You cannot, it's going to go off and do something asynchronously, and you can't await it. You can't wait for the result to come back. And you almost always want to do that in the context of a web application. If you're trying to do something that's truly fire and forget in a web application, do something like thread pool q user work item or something like that, so that you're explicitly telling other developers that come along after you, I want this work to be fire and forget on a background thread, and I don't care about the result. But in the case of a UI application, that's the reason why async void exists at all, is for event handlers. So event handlers, always return void because you can't await the result of an event handler. And so like a button click, for example, and we're going to show this in a second, that's going to be void. Void, button click that takes in sender and args and all that kind of stuff. You can just make that async. You don't have to do anything special. Any event handler in any UI application in C#, you can just add the async modifier onto it as long as it's already returning void and start doing async and await stuff. So you're good to go. And then when you come back, you're going to be, from the async operation, you're going to be back on the UI thread. So that's the case for it, is only use that in the case of a UI application. Async task is equivalent to async void, but it can be awaited. So it's a async feature that you want to wait for it to finish, but it doesn't return anything. And then, of course, task of t returns the generic type t value that when you call await, it unwraps it and returns it back. So I'm going to get into a demo of kind of how to use async and await real quick, kind of an introductory setup of our example app. But do we have any questions so far? Cool. All right, so when I tried to do this demo in Chicago, Visual Studio locked up on me. So I'm going to hope that that doesn't happen today, because things always go wrong in demos. So here we've got a WPF application that has a single window and just an awkwardly placed button that says async. And so we've got an event handler on this for, you see we call button click. And so when we navigate to that, you'll see that we've got private void button click, takes in sender and our args. And so first we're going to say that the button's disabled because we're going to sleep for 15 seconds. And then we're going to say, OK, once we're done sleeping, we're going to set the button to enabled again, right? But can any of you see the problem? Yes, the UI is going to lock up in the thread.sleep call, and the button most likely is not going to be updated to be disabled. So we can just demo that real quick. So let's. OK, so we've got our application. We can move it around, resize the window and everything. It's responsive because we're not doing anything yet. We click the async button. You notice it doesn't get disabled. And I can also no longer resize it. I can't move it around. We've locked up the UI thread. Okay, so I can't maximize it, can't minimize it, can't do anything with it. So the OS is trying to send the window messages, and it can't because because it's unable to respond to those messages. We've locked up the UI thread. So and then we're done, and we've got the button responsive again. Now we can move it, resize it, and everything else. So that's obviously bad code, and just pretend that that was an HTTP request instead of a thread.sleep, right? So let's modify this to be async so that we can kind of allow the UI to stay responsive while we're doing some long-running operation like thread sleep. So if we just change this to async, so this is completely legal, but you see that we start getting the green squigglies that says this async method lacks await operators and will run synchronously. So it's like, telling us we probably should be awaiting something inside of an async method. So what we're going to do is change this to await task.delay, which is the async equivalent of thread.sleep. So almost identical code, right? But we've got the await keyword. Now if we run this, okay. Now notice how it became disabled. We can move the window around while it's doing something. We can resize it because the application stays responsive. And then at some point, once we come back from our task.delay, there we go, the button's enabled again. So imagine that was a progress indicator or something else that you wanted to display to the user while you're waiting on an HTTP request. So let's make this actually an HTTP request. And I'm going to show you this method down here called do something async. So here we've got an HTTP client, and we call getAsync on our local server that we've got, which is running an IIS Express. You see I've got an async demo web project up here in the top right, which is just a simple MVC app. And we're going to get the response of that, read it as a string, and return the results of that. So we've got a task of string, which means when we call await, we're going to actually be returning the string out of that. And so instead of doing await task.delay here, we're going to do await do something async. Okay. And then over here, our home controller, we've got a thread.sleep call in here. This is all synchronous web code. And then we're going to return the string hello. So what we want to do now is we want to actually do something with that. So let's do string message equals await do something async. And we'll do message box show message. Okay. So now we're going to have the same thing happen. So let's get our web server started up. And then now we've got our web server and our WPF application running at the same time. It disables the button. UI stays responsive while we're waiting on that HTTP request to come back. And then, we get the result back. So we've done await to unwrap the result of that async operation. And then as soon as we dismiss the message box, our button's enabled again, and we can do it again if we want. So this is kind of our example application that we're going to use to show some more concepts around async and await and some best practices. Now I know Stacy kind of mentioned yesterday's keynote that you shouldn't use the term best practices. So my presentation is littered with that term. So I guess we've got a slight differing of opinion. But in this case, if you don't follow these guidelines, you can certainly shoot yourself in the foot. So I strongly recommend that you follow these guidelines or best practices or whatever we want to call them. All right, so best practices. So again, we don't want to necessarily async all the things, as we talked about earlier, but if it is something that is going to block a thread and it should be asynchronous, you should make it async. And the important thing to remember about async methods is just because you have an await inside of it, that doesn't mean that the entire method is asynchronous. So in this case, we're coming in from the UI thread, for example, and then we call this do something method, which is not async, and we're not awaiting the result. So this is actually going to run synchronously until we get to the first await statement. So we're going to be blocking the thread all the way until here. And so if this took 10 seconds to return, we're going to be blocking the thread for that period of time. So in that case, you need to think about, especially with UI applications, but also if you're trying to optimize concurrency of a web application, what parts of the code, even though it's an async method, what parts of that method are running synchronously, and which parts are running asynchronously, so that you can make sure you're making the right decisions. So here's a bad practice, is calling .wait or .result on a task. So if you call .wait, basically you're doing something asynchronously. You've got a task and it's going off and doing something in a background thread or waiting on an IO completion port. But because you're calling wait, now you've blocked this thread, which means that it can't get the result back. So if do something async takes longer than perhaps a microsecond to return, then you're probably going to get a deadlock in this case, because you're blocking the thread waiting on a result, but it can't return the result to that thread because you're calling wait. So you are definitely going to end up in a deadlock scenario there. Now there's an exception to this, which is console applications and things that run in a single thread like a console application. So things like a Azure worker role, for example, or any kind of single threaded service. You can call .wait so that you can have things happen asynchronously, but that's going to be at your highest level, like in your public static void main, right? So in that, or actually this is a different example, but in this case, we want to await all the things as well. So just because we're calling an async method, you've got to actually await the result if you want it to, probably most likely do the correct behavior. Again, if you're trying to do something that's fire and forget, do something like thread pull queue user work item so that you're very clear about your intentions that you want it to be fire and forget. But otherwise, in this case, this is going to be fire and forget because it's going to go off and do something asynchronously and then immediately return view in this case. And so most likely that's probably not what you wanted to do. You probably wanted to wait on a result so that you can catch an exception which is an important thing, is if it's fire and forget and an exception happens, bad things can occur. So don't ignore those squiggles in Visual Studio. So if you get those little green squiggles underneath it, if you hover over it, it's going to tell you this method is running asynchronously and probably should be awaited. Okay, now we're getting into a little more of an advanced concept with async and await. This is primarily if you are creating your own async methods or if you're refactoring things out into async methods that are calling other async methods. So this is an example very similar to what we had in our WPF application, where we set our enabled to false. We await do something async. In this case, we're doing it in a finally block, but we're back on the UI thread, and so we can set is enabled to true. But you know, if you're not on the UI thread and you try to call a button that's set is enabled to true, you're going to get an exception saying that you can only modify the state of the UI from the UI thread. So in this case, what we're going to be looking at here is, so button click is calling do something async. And so then this is the implementation of do something async. So we've refactored our multiple await calls out into a separate async method called do something async. And in this case, we're just doing task.delay, but again, pretend it's HTTP request or something else. And so we start out the method on the UI thread because we called it from the UI thread. And then we go off and we await the result, and when we come back, we're back on the UI thread. And so we can modify the UI if we want to, things like that. Await the result, back on the UI thread. Well, that's okay in the case of 2 await task.delays, but what if you've got hundreds of async calls, or even just dozens? What can really happen then is what Microsoft calls death by 1,000 cuts in this case, is you're spending so much time switching back to the UI thread that now you've actually slowed down your UI thread again, right? And so if in this case, we've just got a comment between these 2 awaits. We're not doing it. We don't need to be back on the UI thread. There's no reason for us to be back on the UI thread between those 2 awaits. So if you don't have a reason to be back on the UI thread, which typically is the case in library methods, or if you've refactored out into a separate method where you're just returning results or making sure you do a number of asynchronous operations, then basically you don't want to keep switching back to the UI thread unnecessarily, otherwise it'll start slowing things down again. So what you can do is called configure await false. Because the method task.delay or anything that's awaitable has is going to be a task type, and so you've got the configure await method on it, and then configure await returns itself back a task, so you can await that. So you just got to call .configure await on the end of it with the false as the parameter, and what that says is, you know what, I don't really care to be back on the calling thread once this returns. I can be on a completely different thread. It's your choice. Async method, it's your choice as to what thread we return back on. And so, so in the middle here, between the 2 awaits, we may or may not be back on the UI thread there. And so in that case, we probably, we're okay with that because we're not updating the UI at all. Yeah?
Okay. That works for things that you are doing that you don't need a response now.
No, even if you need the result of the task, it still works as long as you're not having to update the UI. So as long as you're not having to update like a text box or a button or anything in the UI, this could be like string foo equals await, do something async, string bar equals await, do something async. You can still do that. It's just as long as you're not touching the UI and you don't need to be on the UI thread in that case, use configure await false, and then that way it can keep running on a background thread as needed, and you're not getting that death by 1,000 cuts coming back to your UI thread. Oh, and the important thing is, I mentioned, do this inside library methods you write. Do this when you refactor async methods that are calling other async methods. Do not do this from the calling method here. So whatever you do, do not do configure await false here, because otherwise you're going to be coming back not on the UI thread, and when you try to do this, it's going to be an exception, right? So inside, if it's a UI application, inside your event handlers, if it's a web application inside your action methods or whatever else, don't call configure await false within those methods, but do it inside methods that you're calling from that. Yeah?
So configure await is method scope, correct? So
yes.
The calling method, that's where configure await is scoped to, correct?
Yes, because I put it down here and I forgot to mention it, so thank you for bringing that up. Each async method gets its own context. So as soon as you enter the async method, it's got its own context for the lifetime of that async method. So and that captures the UI thread that the context was called from, or captures the thread that the context was called from. And so so basically, let's say the UI thread was ID 1. And then we come back and we're on ID 2. When you call this method, it's going to get a different context. It's going to capture thread 2 and so on. But then when you return back, because you're now back in the calling method, you're on whatever, as long as you haven't done configure await false, you're on whatever the context had captured previously. So another best practice is a cancellation token. So a cancellation token can be generated by a cancellation token source. What it does is it gives you the opportunity to cancel some sort of asynchronous request. And we're going to actually do a demo of this here in a bit. But if you're doing ASP.NET MVC or ASP.NET Web API, you can just add a cancellation token method onto your action method, and ASP.NET knows what to do with that. It'll automatically give you a cancellation token. Now, in HTTP 1.1, whether it's running on certain versions of IIS, that may not end up ever being canceled. Like if you hit stop in your browser, that may not ever end up invoking that. But it's still a good idea because, especially with HTTP 2, with the newer versions of Web API, especially in ASP.NET Core, I know it's got first-class support for that, is that if you try and stop a request, it'll actually invoke the cancel on the cancellation token. And so when you get this cancellation token, you're going to want to pass that to all async methods that you call, if possible, so that all of those async methods that you call, in this case we've got open async and we've got execute scalar async on our SQL connection, that they can cancel if needed. You can also call throw if cancellation requested, which will actually throw a task canceled exception in the case that you want to handle it manually. And so I'm going to do a demo of that. Any questions before we get into the demo?
Do you recommend using that on most of your controller methods? That are async, that you're doing some kind of query on?
Yeah, I mean, today it's not really important if you're doing, ASP.NET on .NET 4.6, and so like I know the new versions of ASP.NET Web API and running on .NET Core are particularly handling that very well. But today, is it super critical today? No, but going forward, it's kind of a good idea that if someone stops a request in their browser, that you're not trying to continue handling that request. As to whether or not that's actually going to get called, today is kind of a question mark. But it's a good idea, especially if you're creating library methods that other people are going to consume, because if they're calling that from a UI application, that's where your cancellation tokens really shine. And so I'm going to show that in the demo. Yeah.
Having a cancellation token looks like it's a good idea if your call doesn't mutate say make any changes to your database or anything. But if the method that you're calling, the web API that you're calling, is doing something interesting, like going out and changing your database, so it's talking to a third-party vendor and recording those results, I would think you would not want it to be possible for that to be canceled.
Depends. It depends on the use case. Also, you could look at transactions. So, say you had multiple SQL queries that were happening. If those are run inside of a transaction and the first one gets canceled, then that's going to be rolled back. So it depends on if you're using transactions, distributed transactions. It depends on what you're doing once you get back from the result of that async or await call. Maybe you're doing something there where if it's been canceled, we truly don't want to continue. So it just depends. So you don't have to use cancellation tokens. If your case, and so that's where, in this case, probably best practice is not necessarily the right term, but it's something to be aware of, certainly, in that if you're creating library methods, you definitely should have a overload of your async method that takes a cancellation token so that you're making that option available to other people. As for whether or not you use one yourself, that depends on the use case. So, all right, so let's look at configure await. So here, back to our example, we've got two await calls happening inside of our do something async, which means that as soon as we get back from the get async call, because we entered this method on the UI thread, we're going to be back on the UI thread inside of here. So if we wanted to update the UI, we could, but in this case, we don't need to. So there's no reason for us to be back on the UI thread, slowing down the UI thread here. So before we do our other await. So in this case, what we're going to want to do is do configure await false. Oh, and then I forgot to show the example of this failing. So if we wanted to do, let's say, button.text, or sorry, content. Come on now.
It's not the name of the button.
Oh, because it's static. Haha. Sure. So in this case, this is completely legal in this case because we're not doing configure await false. So we can update the UI if we need to. But generally, in this case, we don't really need to do that. Probably the caller should be handling that. And so this will work. I don't need to demo that. But if we call configure await false here, and then we'll call configure await false down here. So that when we come back from that await before we return, we're not on the UI thread either because we don't need to be. Then when we run this, and we hit the button. Once it comes back from our HTTP request, we're going to get an exception. Yep. So calling thread cannot access this object because a different thread owns it. So, but in this case, that's kind of what we want. We want to be on a different thread because we don't want to slow down the UI thread. So we're just going to remove this call here. And then now all of this is going to work. We're basically just not going to be on the UI thread when we come back anymore, slowing it down. But we return the string back, and then the UI thread can do whatever it wants with it. Because, again, each method gets its own async context. And so this context has captured the UI thread. This one has captured the UI thread, but we've kind of released it with configure await false. And then we get back here, and we're back on the UI thread again, so we can update the UI. So now I'm going to show the cancellation token. So in order to get a cancellation token, you need a cancellation token source. We'll call this cancellation token source. Okay. And an important thing to know is basically if you're given a cancellation token, that source, you don't want to kind of keep that alive. You want to kind of new that up for each time that you need it. In this case, and this is probably not a good example, but because this could be happening in parallel, theoretically. But we're disabling the button. So we're going to new this up. And then we're going to get our cancellation token. Source.token. Then inside here, we're going to pass that token, so we need to be able to take that. Okay. So we're going to pass that to our async method so that we can cancel it while it's running. And then we need to pass that into our getAsync call. Now, here's one selling point for ReSharper. I'm going to do some free sales for them. Is if you have a method that takes in a cancellation token and you're calling an async method and you're not passing it, it actually gives you a green squiggly warning saying method has overload with cancellation support. That's something that's offered in ReSharper that Visual Studio doesn't give you out of the box. So it's kind of a nice thing to have. It also gives you a built-in refactoring where you can just do pass cancellation token. It'll add it in there for you. So selling point for ReSharper there. So yeah.
Why do you need to make a new token source every time?
Because of how cancellation token source is implemented, the token, you see that we're calling source.token. That's the property on it. And then you interact with the cancellation token source to cancel that token.
So you don't want to keep reusing them for multiple tasks? Is that
Correct.
If you
Yep.
had 3 events on here and you weren't blocking the UI, you want a new token for each of those events. You could be running them simultaneously.
Possibly, unless we wanted to cancel all of them at once.
Sure.
So.
Does it matter that you're using a single source to generate the tokens? Potentially?
Does it matter in what way?
If you had 3 events.
Yeah.
I'll get you after this.
Okay, cool. So wrong keystroke. So I'm going to switch back over to our XAML here, and I'm going to uncomment this cancel button. Okay. So now we've got a way of canceling our asynchronous operation. And so let me add. Okay. So now we've got a way of canceling it, and all we have to do is probably add a little safety thing, but or we can do source question mark that cancel, and that should be it. So this is going to invoke the cancellation cancel method, which is going to tell the cancellation source to invoke cancel on the cancellation token that's passed to the async method. Everybody makes sense so far? All right. So let's go ahead and run this. All right, so we're going to fire off our async call, disable the button, but then, and now we get a task canceled exception, right? So this is kind of what we want it to do. We want it to bubble up an exception so that we can handle it. But you can see that we've kind of interrupted the async behavior. We don't have to wait for the whole 10 seconds for that to finish. Now, of course, yes, it's important to understand that if you're doing a web request, if that's not canceled correctly, that's probably still going to keep on running. But this at least gives you the ability to cancel any future async operations. And so here we're going to wrap this in a try-catch, which if any of the ReSharper people are watching this video, if it detects that there's a cancellation token, it'd be awesome if it could wrap it in a task canceled exception for you, or wrap it in a try-catch to catch a task canceled exception. So, and we're just not going to do anything in that case. So we're going to kind of swallow a task canceled exception, and then we're not going to get to showing the message box. So let's go ahead and run that again. Fire that off. Cool, cancel. Immediately the button's enabled again because we swallowed that exception back on the UI thread, enable the button again. But of course, if we want to allow that to continue, we can. So that's kind of a way of, you notice that I didn't have to do anything other than kind of, having the cancellation token source. In this case, I'm having to do that manually because it's a WPF application. If you were doing a ASP.NET application, like I said, ASP.NET is going to do the cancellation token source for you. So you just got to give it a parameter on your action method. It'll pass that in for you automatically. But we just catch a task canceled exception and pass it along to the async calls that support it. Not all async calls do. Like this read as string async doesn't have a overload that takes a cancellation token because you probably don't really need to cancel that. You probably are going to be more concerned about canceling I/O things like HTTP requests. But the other thing I forgot to mention is that if you wanted to explicitly say that you wanted to handle the cancellation token manually, you can do token.throw if cancellation requested, and then that'll actually throw a task canceled exception if it's at that point if it's been canceled. Yeah.
So if you're passing the cancellation token into your getAsync, does that propagate up to your home controller? So can you catch it? So if you need a cancellation token there, how does that work? How does that work through?
So the task canceled exception will be called by the async methods, and so because of the context and unwrapping the context at each method call, that just bubbles up like a normal exception, and then you can just do try catch around that. Now, in the case of ASP.NET, you don't really need to try catch that task canceled exception unless you specifically need to. You can just let that bubble all the way back up to ASP.NET, and then it might invoke your server error and might show up in your error logs, but depends on how you want to handle that. So. All right, so I've got a few more minutes to kind of get through. This is the end of my demos. So I'm going to get through some examples of async and await showing up in other languages. So I've kind of shown you how it works in C#. These other languages are very similar. JavaScript, again, kind of a before and after. Even though it's before, I'm using some ES6 features like lambdas and string interpolation, and the fetch API. But here we've got two functions: get post, get comments. And so you guys have probably seen code like this in JavaScript, get post.then, and then we get our posts back, and then get comments.then comments, right? So you kind of get the nested Lambda effect. Well, JavaScript has got async and await now too. Before I get there, here's what it looks like before with error handling. So this previous example isn't too bad until you try to handle what happens if the server throws an exception or returns a 404 or anything else. So in this case, we've got to add .catch, and then we get an error, and so we can handle and do alerts or whatever else we need to do to alert the user that something went wrong. So you see the code gets more and more complex when you try to add error handling into this. So JavaScript now has async and await. So you can do async function get post, and then you can do await inside of it. Same thing with our get comments. And then down here, we've got show post is our async function. We can do await inside of it. And then we get our same try catch behavior, so we don't have to do .catch on a promise. We can just do our multiple await calls, here, and be able to do that in much less code than the nested Lambda approach. And so last month, it actually became a stage 4 proposal by the ECMAScript committee. So async and await is finalized in JavaScript. So that means once it starts popping up in browsers, you're good to go to use it. It's already in Edge, so you can use it in Edge today. But you can also use it in Babel. So right now, I think it's still, you have to use the stage 3 preset in Babel because it was stage 3 up until last month. But you can use it in Babel, and it'll translate your async and await calls to use generators, which is a topic I don't want to get into right now. But it's very, very cool. I'm using it in a production application in JavaScript today. Works very well. C++ is getting async and await as well. So this is something that the Microsoft C++ Visual Studio team is kind of pushing pretty hard in the C++ community. And if you guys haven't noticed, C++ lately has been an awesome community. For a while there, it was kind of dead almost from like 98 until 2011. And as they were trying to get the C++ 11 standard, which kind of became very, very large. But since then, we've had C++ 14. Next year, we've got C++ 17 coming out. So they're getting to regular release cadences. I encourage you guys to look at the C++ community and their meeting notes and everything and what they're doing. Really, really cool stuff. In this case, again, not necessarily using any kind of best practices because we're calling wait and whatnot, but we're in a console application. But here you can see an example of using await, even though here it's __ await because it's kind of a still developing feature. By the next version of Visual Studio, that's expected to just be the await keyword. And then we've got task of void, which is equivalent to task without the generic type parameter. You can do create task and give it a lambda. This is the funky lambda syntax in C++. And so if you want to do this, you have to hash include ppl await.h. Now, resharper says we're not using that. I can easily remove that reference. And then resharper doesn't know what the __ await keyword is. But it works, it compiles, it runs. So once it kind of becomes a little less experimental, we'll be able to see that being used more in the wild. And then there's also the stud future of T to look at if you guys are C++ folks. And then depending on which version of Visual Studio, I think you have to use the /async command line flag, which you can set in your project properties. Python has async and await now too, as of Python 3.5, I believe. So you can do async def do something async. You can do the await keyword. If you want to, from a Python console application or any time you need to actually kind of invoke an async method, you import async IO, and then you get this get event loop, which essentially is getting your main thread, and then you can do run until complete on that feature that's returned from there. So Java. So you go to the JEP, which is the JDK enhancement proposals, and you Control F for async, and no. So they're not even talking about adding async and await to Java at this point. So it's not even on the roadmap, which is extremely unfortunate. I do Java development in Android. I would love to have async and await on Android without having to use Xamarin or anything else. And so unfortunately, it's not coming to Java anytime soon, or at least no one's talking about it. But Kotlin, so by JetBrains, so you can actually convert Java files to Kotlin. It runs on the JVM. It has some really cool features. It's a very similar language to Swift, if you guys have done any iOS programming. But basically, they are actively working on it on async and await and yield right now with coroutines routines for Kotlin. And you can do Kotlin programming on Android as well. Swift, they're talking about it. Here's an example. This is a slightly older one, example of what this might look like in Swift. There's some active proposals at these links of people trying to get this into Swift. They're now talking about it for Swift 5. Swift 3 is coming out this fall. They're saying it's not going to be ready for 4, so it'll be in Swift 5. So it's going to be a ways down the road for Swift, but at least they're talking about it in the community. So. And I think that's it. Yep. So again, check out John Skeet's blog. If you search for the category of EduAsync, that gives you a good series of posts about implementing async under the hood, as well as Stephen Cleary in the .NET community. He's an awesome resource for everything async and await. This is an older post back from 2012, excuse me, which is where I got a lot of the information about configure await and everything from him. And that's all. So thank you.